All right, this is the last section for Chapter 2, and this is dealing with rates of change and tangent lines. This is hopefully going to tie together everything that we've done so far in Chapter 2, dealing with limits, and bring us towards Chapter 3, which deals with derivatives. The slope between two coordinate points, x comma 1, or x1 comma y1, and x2 comma y2, is defined as the change of y, y2 minus y1, over the change of x. And this is something that you've been doing since probably 8th grade, where you just do the change of y over the change of x. And traditionally we talk about slope as m. Another term for slope is average rate of change. Slope is technically telling us, on average, over an interval, how much are the y values changing compared to the x values. Okay, it's a rate. And I will use AROC, average rate of change, as shorthand notation. So for example 1, we were talking about a function, f of x equals 1/2 x squared plus 1. The first thing I want you to do without a calculator is to plot the coordinate points 2 comma f of 2 and 4 comma f of 4. So I'm going to have you pause and do that right now, please. Okay, so I plugged in x equals 2 into the function, and I get a y value out of 3, which makes the coordinate point 2 comma f of 2 equal to 2 comma 3. Additionally, for 4 comma f of 4, I plug in the x value of 4 into the function, and I get out a y value of 9. So I've plotted these 2 points here. Here's 2 comma 3 and 4 comma f of 4. Now, this lies on a parabola that is vertexed at 0 comma 1, and it goes through these points. If I can do that, there we go. So the 1/2 is going to make this less steep than a traditional parabola with an x squared that has a coefficient of 1. So this is less steep. Now when I want to determine the average rate of change of the function, average rate of change is just slope. I want to know on average how this function changes its y values over the interval from x equals 2 to x equals 4. So you're just going to use the slope formula, and f of 2, you can do this either way. It can either be f of 2 minus f of 4, or it could be f of 4 minus f of 2, but then you just have to be consistent in the denominator. If 2 came first in the numerator, then 2 would come first in the denominator. F of 4 and f of 2 we just determined up above. F of 2 was 3, and f of 4 was 9. And then on the denominator we have a -2 value. So overall, we're getting a -6 divided by a -2, which gives us a value of 3 for our average rate of change. So what you're basically saying is, on average, the y values are increasing by 3 for every one value of x. So lastly, what kind of line would it be if we connected our two coordinate points? And you might have heard this word from geometry. This is called a secant line. So, but what do we do if we want to know about the rate of change at just one point? Okay, so we're gonna scooch up the paper here for just a second. So if we want to know the rate of change at only one point, I would ask you to write the slope equation using the coordinate points x1, y1, and x1, y1. It's the same point. So our slope, which is our AROC, and that's going to equal the change of y over the change of x. And of course we're getting a 0 over 0. We all know that that's not allowed. Okay, so this is an indeterminate form. So the prediction here, I want you to write something down. How could you estimate the slope at just one point? Notice up above, I had two coordinate points that I was able to actually come up with to find the slope. You just use the slope formula. But if you're only using one coordinate point, what's a good way to estimate And I'm going to point out the word estimate here. This is not going to be an exact thing yet. How would you estimate the slope at one point? So write down your ideas and come back. Okay. We'll talk about this in class, and if we haven't discussed it already, I know we have had discussions earlier in this week about it, but I want you to think about your prediction. We're going to talk about this when we come back to class tomorrow. All right, so when we talk about some vocabulary here, the secant line connects two coordinate points. Okay, and I showed you a picture of that on the previous page. It could be a coordinate point here and a coordinate point here, and as long as you connect those guys, that would be considered your secant line. The tangent line, it's only at one location, so it's at only one point. And if you remember a tangent to a circle, it looks like it bounces off. So when I draw a tangent line to the exact same function, the idea when you draw a tangent line, and a lot of students have a tough idea with this concept, I want you to start at the coordinate point, and I want you to go a little bit in the direction of the function and a little bit in the direction of the function that way. So when you move in the function's direction, a little bit to the left and a little bit to the right, you create this small little segment. Now if you were to continue that line, that's what's considered your tangent line. Okay? It might go through the function at other locations, but the idea is that at that one coordinate point, it touches the function and then bounces off. And if you have questions about that, I can give you some more examples tomorrow in class about how it might go through the other part of the function. Okay, but you're just looking to draw a teeny little segment in each direction from the coordinate point and then extend it. So it's at only one point. The normal line is perpendicular to the tangent. Okay, so it is the opposite reciprocal slope. Okay, if you remember from geometry, anytime you draw two lines that are perpendicular to one another, that's what the normal line would look like. The slopes would be opposite reciprocals. Okay, so how does this all tie in together? When we use the word average rate of change, we are talking about slope between 2 points. And 2 points that are connected are on a secant line. So you can tie it all together and say that this is really the slope of the secant line. And I'm going to emphasize that there are 2 points involved when you do this. That goes along with the word average. It happens over an interval for x. Now when I talk about instantaneous, I want it at just one x value. So this would be the slope of the tangent line. Okay, there's only one point involved on the function. Okay, so I'll probably be asking you about this tomorrow. Just make sure slope of the secant has two coordinate points connected, and you use the slope formula. As far as the slope of the tangent line, there's only one point that we'll be using. Okay, so I'm just going to write the formulas over here. For average rate of change, you just do the change of y over the change of x. Okay. It is more commonly written as f of b minus f of a all over b minus a. And the a and b in this case are the x values that you are talking about. So if I move this up just a little bit, I'm kind of jumping around a little bit here. If I go back up to the graph up here, your a is your x value at your left endpoint. Your b is the x value at the right endpoint. So this would be considered b, and that would be considered a. So f of b indicates the y value. F of a indicates the y value at x equals a. So this is just change of y over change of x. The instantaneous rate of change is a little bit different. A limit is involved because what we're trying to do